Hey there! Ready to dive into some seriously cool math? We're talking hidden patterns in numbers, equations that have puzzled mathematicians for centuries, even connections to music and art.
It's amazing how something that sounds so complex can actually be broken down into, pretty simple ideas.
So let's start with the basics then. What exactly ISE, a binary quadratic form?
Imagine a simple equation. You've got your x's and y's, but with a twist. We've got x spay, maybe an icy term, and a y, all dressed up with numbers in front. Those are the coefficients, like secret ingredients. They give each form its unique flavor.
So it's like a recipe, but instead of flour and sugar, we're using X's and Y's.
Exactly. Changing the amounts in a recipe changes the final product, right? Those coefficients. They determine what makes each binary quadratic form special. For instance, the form x ped plus y, that's all about sums of squares. But then you've got something like x ped 2y power that leads us to Pell's equation. It's fascinating stuff.
Pell's equation. Okay, now you've got my attention. Sounds like we're about to embark on a mathematical treasure hunt.
It does, doesn't it? And speaking of treasures, one of the first things mathematicians wanted to do with these forms, figure out if two forms, just at first glance they look different, were actually the same, just disguised with a bit of mathematical camouflage.
So like identical twins dressed up in different outfits.
Precisely. Mathematicians call this equivalence. They came up with specific rules to determine if you can rearrange one form into another using, clever substitutions and transformations.
Can you give us an example? Walk us through this transformation magic.
Absolutely. Take the forms x psi plus 4 by xi plus 2i beta plus 4 by y 2y level. At first glance, totally different, right? But with a bit of mathematical wizardry, you can transform one into the other, proving they are, in fact, equivalent.
Wow, that's so cool. It's like they're two sides of the same mathematical coin.
Exactly. And once you understand equivalence, you can start asking even more interesting questions, like if I give you a specific number, can you find values for x and y that make the equation true?
So it's like a puzzle. You've got the equation, and you're trying to find the missing pieces to make it work.
You got it. That's representation. Exploring which numbers can or cannot be generated by a particular binary quadratic form. And this is where things get really interesting, historically speaking.
Okay, I'm hooked. Take us back in time. Who were some of the mathematical pioneers who first grappled with these ideas?
Well, imagine traveling all the way back to 3rd century Greece. You meet Diophantus, a mathematician fascinated by sums of squares. He pondered this question. Can you represent any odd number as the sum of two squares using the form x store plus y?
So if we take the number 25, for example, we can represent it as 3 adogit plus 4 deret, right?
You're a natural. But what about the number 7 or 19? Try as you might, you won't find two perfect squares that add up to those numbers. Diophantus was fascinated by these patterns, why some numbers worked while others didn't.
It's like he was trying to crack the code of numbers, searching for those hidden relationships that govern their behavior.
Precisely. And this quest to understand representation, it's captivated mathematicians for centuries. In fact, it leads us to another intriguing puzzle, Pell's equation. Imagine trying to find integer solutions for an equation like this. 1 equals x serio 2y mam mortis. Might seem simple, but it turns out there are infinitely many solutions.
Infinitely many. Hold on. How can an equation have an endless number of solutions?
It's like a mathematical magic trick. It highlights the surprising depth hidden within these seemingly simple forms. You see, starting with one solution, you can generate an entirely new solution using a clever formula. And then, using that new solution, you generate another, and so on. An endless chain of solutions.
Wow, that's mind-blowing. It's like a mathematical, fractal, infinite complexity arising from a simple set of rules.
It's no wonder Pell's equation has fascinated mathematicians for centuries. And as we delved deeper into binary quadratic forms, it became clear we needed a way to organize this vast and intricate landscape.
Like we've stumbled upon a vast, unexplored jungle, and now we need a map to navigate its hidden pathways.
Exactly. And luckily for us, a brilliant mathematician named Lagrange came along and provided the compass and map we needed.
Lagrange. Now, there's a name that echoes through the halls of mathematical history. What was his contribution to this story?
Lagrange. Oh, he was a true visionary. He recognized that while there are infinitely many binary quadratic forms, there's a way to group them, into a finite number of families based on their underlying structure.
So Lagrange gave us the Dewey Decimal System of binary quadratic forms.
Yeah, kind of like that.
That's amazing.
Yeah.
But how do you even begin to categorize something as, well, abstract as a mathematical equation.
That's where Lagrange's brilliance really shines through. He introduced this concept of reduction.
Reduction.
It's a method for finding the simplest, most elegant representative of each family, or as mathematicians call it, each class of forms.
Okay, so it's like finding the most efficient way to pack a suitcase. You're not changing the contents, just organizing them in a way that makes the most sense.
Exactly.
Yeah.
Lagrange, he found a way to take any binary quadratic form and through a series of transformations, reduce it down to like a standard form. A standard form that represents its entire class. And get this, he proved that for any given discriminant, which is a special number that helps classify these forms, there are only a finite number of these equivalence classes.
Discriminant. Okay, you're going to have to break that one down for me. It sounds kind of ominous.
It's not as scary as it sounds. Think of the discriminant as a sort of fingerprint for each binary quadratic form. It's a number, you can calculate it from the coefficients, and it helps determine some of the form's key properties.
So the discriminant is like a secret code embedded within the form itself. And Lagrange figured out how to use this code to categorize them into a finite number of families.
That's the gist of it. And this led to a very important concept, the class number. For any given discriminant, the class number tells you exactly how many unique families or classes of forms exist. It's like having a directory. It lists all the different categories in our vast library of binary quadratic forms.
So thanks to Lagrange, we've gone from like feeling lost in a mathematical wilderness to having a compass, a map, and even a library catalog. That's incredible progress. But our story doesn't end there, does it?
Not at all. Lagrange, he laid the groundwork. But it was another mathematical giant, Carl Friedrich Gauss, who took these ideas and amplified them to a whole new level.
Gauss, the prince of mathematics himself. I can only imagine what he brought to the table.
Gauss was, well, he was a force of nature. He took Lagrange's concept of composition and generalized it, figuring out how to combine forms even if they had different discriminants. He developed genus theory, which gave mathematicians this powerful new toolkit for understanding the structure of class groups. He essentially took a magnifying glass to the world Lagrange had mapped out and, revealed even more intricate details and connections.
It's like Gauss took a beautiful melody and orchestrated it into a full-blown symphony.
That's a great analogy. Gauss's contributions were profound, really far-reaching. He opened up entirely new avenues of research avenues that, continue to be explored to this day.
So we've journeyed from ancient Greece, with Diophantus pondering sums of squares, to 18th and 19th century Europe, where Lagrange and Gauss brought order and structure to this, seemingly chaotic world of binary quadratic forms. It's amazing to see how each generation of mathematicians built upon the work of those who came before, pushing the boundaries of knowledge further and further.
It really highlights the collaborative and cumulative nature of mathematics, doesn't it? It's a tapestry, woven together by countless minds over centuries.
Absolutely. But I have a feeling our mathematical journey isn't over yet. Where does this story lead us in the 20th and 21st centuries? What new discoveries and breakthroughs awaited those who dared to venture further into the world of binary quadratic forms?
Well, get ready for even more surprises, because the story takes some unexpected turns. In the 20th century, with the rise of computers and new areas of mathematics like topology, algebraic geometry, binary quadratic forms, they found themselves at the heart of some truly mind-boggling research.
Okay, now you've really piqued my curiosity. Tell me more about these modern-day explorers and the uncharted territories they mapped within the world of binary quadratic forms. So we left off with Gauss, right? He really shaped our understanding of these binary quadratic forms. But math, it's never really done, is it? What happened next?
You're right. The exploration never really ends. The 20th century, well, it brought a whole new set of tools, new perspectives. I mean, Lagrange and Gauss, they had to do all their calculations by hand. Suddenly, we have computers entering the scene.
That's a game changer for any field, but especially math, I'd imagine.
Absolutely. A mathematician named Daniel Shanks comes to mind. He was a pioneer in using computers to, tackle number theory problems. Binary quadratic forms. Oh, they were right up his alley. He developed something called infrastructure.
Sounds complicated.
It is a bit. But imagine this. You're trying to explore this vast, dense forest. Shanks' infrastructure is like building, a network of paths and bridges through that forest. Suddenly you can navigate much faster. You discover hidden connections that, well, we wouldn't have seen otherwise.
So he sped up the exploration process like exponentially. What kind of new insights did that lead to?
It revolutionized how we study class groups. those families of forms Lagrange introduced, we could suddenly calculate class numbers for much larger discriminants. This revealed hidden patterns, pushed the boundaries of what we knew about these forms.
It's like upgrading from a magnifying glass to a high-powered microscope, right? You see so much more detail. Were there any other aha moments in the 20th century that really, shifted our understanding?
Definitely. Don Zagier, another brilliant mind. He came up with a completely new way to do reduction. That process Lagrange developed, to find the simplest representative of each class. Zagier's method always was more efficient, and it had these surprising connections to other areas of math. Really interesting stuff.
It's always fascinating how someone finds a new way to approach a problem that's been studied for centuries, there's always another path to discover, even in well-trodden territory. Did this new perspective, did it change how we viewed binary quadratic forms?
We definitely added another layer of, richness. And then there's John Conway, a mathematician known for his, well, playful but profound insights. He came up with these visual representations. He called them topographs. Imagine a landscape where each point represents a different form, and the contours of the landscape show how they relate to each other.
So he took something abstract, these equations, and gave them a visual form. That's incredible. Did that lead to any new discoveries?
Absolutely. Conway's topographs, they provided a new lens. Through that lens, we could understand the structure of binary quadratic forms and their connections to other areas of mathematics, hyperbolic geometry, for example. It was a beautiful example of how different branches of math can just illuminate and enrich each other.
It's amazing how something that started with simple equations about squares and numbers has led us to these complex, almost artistic representations.
And the surprises don't end there. Manjul Bhargava, a more recent Fields Medal winner, he found this incredible link between binary quadratic forms and cubes.
Cubes, like the three-dimensional shapes, how is it even possible?
It's a bit too intricate to explain here, but Bhargava's work, well, it revealed this deep, unexpected connection between these forms and geometric objects. Really, it's a testament to the interconnectedness of mathematics, how these seemingly unrelated concepts can be linked in the most surprising ways.
This entire deep dive has been, honestly, one amazing revelation after another. We started with what seemed like this niche topic in math binary quadratic forms and uncovered centuries of discoveries, rivalries, aha moments. It's clear that even today, there's still so much we don't know.
That's the beauty of it, isn't it? Each new discovery, it opens up new questions, new possibilities. What started with Diophantus, just trying to represent odd numbers, it's led us to cutting-edge research, number theory, geometry, and beyond.
So for our listeners out there, the next time you see a seemingly simple equation, remember, it could be the gateway to a hidden universe of mathematical wonders. You just have to be willing to dive in and explore.